Dear friends, this is the lecture number 5 of electromagnetism, the last lecture of this chapter. Today we'll discuss about galvanometer. In the previous lecture, I had told you when a current carrying coil is placed in uniform magnetic field, it experiences torque. It rotates inside the magnetic field. This is the principle of your electric motor. Also, this is the principle of this galvanometer. Torque acts on this coil. Tau is equal to bina cos theta. You just recall bina cos theta. B-I-N-A cos theta. If theta is the angle made by the coil with magnetic field, surface of the coil with magnetic field. Then also I had told you that torque can be written as a bina sine phi. If sine is there, then phi is the angle made by the aerial vector of the coil with the magnetic field. What is theta? What is phi? We have discussed clearly. So today we will discuss about galvanometer. You all have seen this galvanometer in your practical lab. Galvanometer. You have seen this galvanometer in the practical lab. So what is its function? Why we use one galvanometer? Galvanometer is a device which is required to detect presence of current in a wire. Will connect it in series in the wire. If the galvanometer pointer deflects, then current is there. If the pointer doesn't deflect, then no current passes through that wire. So galvanometer is a device, electrical device used to detect presence of a current. Sometimes it can measure very small current. Also, it can measure very small current. Already you have used this galvanometer in the practicals in your lab, as well as you have connected this galvanometer in Wheatstone bridge to know the presence of a current in one arm. Also, you have connected it in meter bridge to know whether current passes or not. Also, you have connected it in potentiometer to find the null point. So galvanometer is a device which is used to detect presence of a current or to measure very small current. What is its principle? Just before I told you, when a current carrying coil is placed in uniform electric field, it experiences torque. But I'm telling you one thing, you mark it. Common mistake. Sometimes some students do one common mistake. What they write in exam in principle? They will write, when a current carrying conductor is placed in uniform magnetic field, it experiences torque. Can you mark in this line where I did the mistake? Again I am repeating the line. Listen carefully. Each word, what students do, at which point, in which word students do the mistake while writing an exam. Many students, those do not have the focus on study, those who read superficially, they do this type of mistake. What? Sometimes they write in exam, when a current carrying conductor is placed in uniform magnetic field, it experiences torque. Can you able to mark? You can listen it again, going back in the video, and try where the mistake is there. If you got it, then it is very good. Now I'm going to tell you where is the mistake. I know all of you got it. Conductor should be replaced by coil. Conductor never experiences torque. Conductor experiences force. A single conductor experiences force. But when it is in the form of a loop, it bounds some area. It is from form of a loop. then torque acts. That loop may be rectangular loop, that may be circular loop. Okay, so you have to write when a current carrying coil, not conductor. Remember, you will not do this type of common mistake in exam. So this is about the principle of galvanometer. Let's come to its construction. From the principle, construction is very clear. It must consists of one coil. Must consists of one coil. Coil should be made up of a good conductor. Like we cannot afford money to take silver, though silver is the best conductor of electricity, but we cannot make the coil in silver. If we make the coil in silver, then the galvanometer will get in jewelry shop. Okay, so galvanometer coil is generally made up of copper. So coil is made up of copper. One coil is there in the galvanometer having many number of turns. More is the number of turns, more is the torque, even for a small current, because bina cos theta. If I is less, if number of turns is more, then torque will be more. So a coil, it consists of a copper coil having many number of turns. Second is, inside the copper coil, whether it is hollow or some material is there, that is also important. If you take hollow means air as medium, then no problem. But if you replace it by soft iron core, then you will get a lot of advantage. Soft iron core is required there. Generally soft iron core is made. So soft iron core, its core contains soft iron. The coil core contains soft iron. What is the advantage of soft iron? Soft iron is a material which, when you will keep in the core, its importance is like this. Try to understand this one. The magnetic lines of forces, even if it's passing like this, and if soft iron is here, it will drag the magnetic lines inside it. It will drag the magnetic lines of forces inside it like this. It will drag its lines of forces, those who pass nearby inside it, and the density of magnetic field lines increases. Flux density increases, means magnetic field increases. Why we are doing like this? Only for this one you see, bina cos theta. How for, even if for a very small current, how will get more torque so that the coil will deflect? How will get more torque? We try to increase the magnetic field by the help of the soft iron core, because it increases flux density, the density of lines of forces. Also it has another advantage. I will tell that advantage. Then the small current, a number of turns I told you, to make as much number of turns as possible. Okay, area, while increasing area, we will think about it, because increasing area will increase the torque, but another way the galvanometer will be bulky. The galvanometer size will increase. That's why there is a little restriction while increasing area of the coil. So then about cos theta, we will go to that one, cos theta. To get maximum torque, what happens to this cos theta? For which value of cos theta this torque will be maximum? If cos theta will be maximum, torque will be maximum. If cos theta is a maximum value of cos theta is 1. If cos theta is 1, then what is the value of theta? Theta is 0. So for theta 0, torque is a maximum torque. How will you make the theta 0? So that when the coil rotates, inside the magnetic field, when coil rotates, but at every moment, angle between magnetic field and aerial vector, angle between magnetic field and surface, this angle as theta cos I have taken, this is the magnetic field and the surface. Angle between magnetic field and surface should be always 0 for any orientation of the coil. But how will I achieve that one? How is it possible? For that we will take the magnetic field. Third one, it is concave shaped pole. Concave shaped pole pieces we will take. Concave shaped pole pieces to provide magnetic field. So this concave shaped pole pieces and soft iron core both help to make theta 0, and at that time the magnetic field is called as radial magnetic field. Radial magnetic field, this is very important point here. Remember, radial magnetic field. What is the importance of radial magnetic field? In exam question will come. What do you mean by radial magnetic field? How radial magnetic field can be achieved? Three things I told you. First is, what do you mean by radial magnetic field? The magnetic field is said to be radial if for any orientation of the coil, suppose you see, I am showing you, suppose this one, this is your serial mode, suppose this is a coil, okay, if this is the coil and magnetic field is applied here, this concave shaped pole pieces should be like this, concave shaped pole pieces. So when the lines of forces will come, this is the coil inside it rotates, coil inside it rotates like this. When the coil rotates inside it, what happens? So angle between magnetic field and surface of coil should change, but due to soft iron core and the concave shaped pole pieces, that angle doesn't change, that angle always remains 0. That's why the field is called radial and torque is maximum. How it is 0? You see, this is the coil, I'm showing you. Lines of forces comes, inside it soft iron is there. When the lines of force should go like this, but due to soft iron, lines of forces, those lines of forces which go like this, it will enter inside it. The lines of forces which should go like this will enter inside it. Even if when the coil turn, magnetic lines of forces again enter in the surface. The lines of force which comes and enter in the surface and it goes out. So always the lines of forces remain inside on the surface of the coil. Always lines of forces remain on the surface of the coil. Inside it lines of forces pass. Okay, due to this soft iron core. Soft iron core has two advantages. Remember, what is the advantage of soft iron core? First one is to increase magnetic field strength. To increase magnetic field strength, it has two advantages of soft iron core. First one is to increase magnetic field strength. And second advantage is to make radial field. It has two advantages to make the field radial. Soft iron core. In exam question will come. What is the advantage of soft iron core? The lines of force which comes, which should go like this, due to soft iron core it enter inside it. It drags the lines of forces to the surface. When it rotates, also it comes to the surface. When it rotates, also it goes to the surface. Lines of forces always remain on the surface of the coil. Always remain on the surface of the coil. So, angle between magnetic field and areal and surface angle between magnetic field and the surface of the coil is always 0. Torque is maximum and the field is called as radial field. You got the answer of the questions. First, what do you mean by radial field? The magnetic field is said to be radial because for any orientation of the coil, angle between magnetic field and surface of the coil is 0. Why radial field is required? When theta 0, cos 0 1 means maximum, torque is maximum. So why radial field is required? To get maximum torque. How will achieve the radial magnetic field? By the help of soft iron core and concave shaped pole, we can achieve radial magnetic field. Three things I told you. What is radial field? What is the advantage of radial field? How radial field can be achieved? So after that, in construction, another point is there. One spring is connected. one spring will be connected to the coil. Below the coil, one spring will be connected. And the whole arrangement, this is the main parts of this galvanometer: coil, soft iron core, concave shape pole pieces to provide magnetic field, and spring. Then in Western type galvanometer, galvanometer also are of different types. Moving coil galvanometer, one is moving coil galvanometer, MCG. The moving coil galvanometer arrangement is different. The deflection we get in moving coil galvanometer in different way. How we get the deflection, if I tell you, that is not in actually CBSE course, but I want to share with you in that. If this is the coil, this is the coil rotate. Coil, that magnet, that coil, it's hung by a wire. That wire is made up of phosphorus bronze by one wire. When the coil rotates, the wire rotates. How will get the deflection? Deflection will get like this. So just below the coil, there will be one bulb. Below the coil, there will be one bulb, and here in the wire, there will be a mirror. There will be a mirror in the wire. Bulb is not below the coil. The bulb will be at a 1 meter distance. So you see, from this the coil, at a distance of 1 meter, one scale will be there. One very long horizontal scale will be there. This is the coil. From this, at 1 meter distance, one horizontal scale will be there. Below the scale, the bulb is there. Below the scale, not below the coil, sorry. Below the scale, one bulb will be there. Very narrow slit. From the slit, the light will come. It will be hung by a wire like this. On the wire, there will be a mirror. Very small mirror, by the help of a gum we will fix. And from the bulb, narrow pointed light will come to the mirror. And on the mirror, when the light falls, the reflected light will fall on the scale. The reflected light will fall on the horizontal scale. When the coil rotates, see, the mirror will now rotate and the reflected light will rotate. Reflected light will rotate on the horizontal scale. So like this, you see, the coil rotate, the wire rotate, the mirror also rotate, and the reflected light will rotate like this. It will rotate on the wire. This is moving coil galvanometer. It requires a shape around 1 meter long. Arrangement is required. That is called lamp and scale arrangement. Okay. So MCG, moving coil galvanometer. But those arrangement, that type of arrangement is not in CBSE board. So in CBSE, what you have? You have Western type of galvanometer. What Western type of galvanometer? It's a very easy arrangement. Why will go to lamp and scale arrangement? If this is the coil rotate like this. You just fix a pointer on the coil. You just fix a pointer on the coil. If you fix a pointer on the coil, what happens? When the coil rotate, the pointer also rotate. You see. Suppose this is the coil now. I am showing you. If this is the coil, then when the coil rotates, the pointer will rotate like this. Okay, so like this the pointer will rotate. So that type of arrangement you can see what is there inside the galvanometer, just opening it. So this is about the different parts, and all the parts are kept in a glass covering so that outside air, due to outside air, the coil will not deflect. Okay. So this is about the construction. Now come to how it works. Even for a small current, that coil deflects very easily, because I told you number of turns more, theta is 0 to get maximum torque, radial field, so that torque deflects easily. So deflecting torque tau is equal to beta. Deflecting torque tau is equal to beta cos theta. But I told you for radial magnetic field theta is equal to 0. So what about this torque? Torque is equal to beta. You got it? Torque is equal to Bina. So this is the deflecting torque. Okay. So due to this torque, that coil deflects. When the coil deflects, what happens there? The spring is connected. One spring is connected there. When the coil deflects, the spring now rotates. The spring now rotates. I'm just telling you one thing. You might have done in your childhood in swing. If no one is there, suppose no one is there to push you, then what you do? In swing, suppose you are sitting alone, what you do? Sometimes you rotate around yourself. When you rotate around yourself, you can able to rotate continuously like this in a particular direction? No. When you rotate in a particular direction, after some time what happens? It gets tight. Then what you do? You just lift your leg from the ground. Then the swing will rotate you in the opposite direction. Then the swing will rotate you in the opposite direction. You all have done in the childhood this one. So what it does? The swing, you rotate the swing in a particular direction by the help of your leg keeping on the ground. And when it gets tight, you just lift your leg, then the swing will rotate in opposite direction. So what you rotate by the help of your leg, that is called deflecting torque. But when the swing rotates, that is called restoring torque. Swing rotate you, that is called restoring torque. The same thing happens here. What happens? When you rotate the swing, when you rotate by the help of your leg, keeping your leg on the ground, when you rotate it, the swing opposes you. The swing opposes you because every wire, every substance, the elasticity nature has the property to oppose. When you stretch it oppose, that is elasticity. When you rotate also, that is elasticity. When you rotate that swing by the help of your leg, touching the ground by the help of your leg, then the swing opposes you. That torque is called restoring torque. You apply deflecting torque, swing apply restoring torque. But swing can't, because your restoring torque is more. So you keep on rotating, the swing also keep on opposing. But restoring torque depends on angle of rotation. Angle of rotation. When more and more, the angle of rotation become more and more. When you keep on rotating, the angle of deflection, the angle of rotation increase. When angle of rotation increase, restoring torque also increase. I'm telling you, restoring torque depends on angle of rotation, phi. I'm telling you. And angle of rotation, phi, I have taken phi angle of rotation, but restoring torque for unit angle of rotation, that's called torsion constant, K. K is one quantity, remember. This is the deflection, restoring torque per unit angle of twist. Restoring torque per unit angle of twist, that is constant for a particular material. K. Okay, that is constant. So if K is the restoring torque for unit angle of twist and you rotate it for angle phi, then the total restoring torque comes how much? K phi. Total restoring torque comes here K phi. More is the phi, more is the restoring torque. If phi increases, then the restoring torque increases. Okay. Phi increases, restoring torque increases. You just recall, when you rotate in the swing, deflecting torque you apply, swing apply restoring torque, but initially easily you can rotate because restoring torque is less, because phi is less. Phi is less because restoring torque is less. Okay, but when you rotate it more and more, phi increase, restoring torque increase. After some time, restoring torque will be capable to oppose your deflecting torque. At that time, what happens? You apply deflecting torque, spring apply restoring torque. When deflecting torque and restoring torque will be equal and opposite, they are always opposite. But when they will be equal, then the swing you can't able to rotate the swing. You can't able to rotate the swing. Equilibrium comes. Equilibrium comes, you can't able to rotate the swing. That is called equilibrium. The same principle, the same concept is applied here. What is the same concept applied here? You see, this tau bina cos theta is the deflecting torque. Okay? So, bina cos theta, and for radial field it is now bina. It is now bina. Then, when this deflecting torque rotates, the spring which is connected here, that opposes, that develop which torque? Restoring torque. That develop restoring torque in spring, and K is the restoring torque for unit angle of twist. Just before I told you, if phi is the angle of a twist, phi is the angle of a twist, then total deflecting torque is how much? K, I am telling you, deflecting torque per unit angle of twist, and phi is the angle of deflection. Then total restoring torque is equal to K phi. And when deflecting torque is equal to restoring torque, then the galvanometer coil will not rotate. Question is coming to your mind. Question is coming to the mind of some students. If due to by this principle that when current pass the coil rotates, then why the galvanometer coil should rotate? If the coil rotates, why the pointer is going like this and coming to rest? The galvanometer pointer deflects and comes to rest. Why this happens? Why the galvanometer pointer goes and comes to rest? This type of question comes to the mind of students. Why? Due to this reason. Deflecting torque in this direction, restoring torque in the opposite direction. When the deflecting torque will be equal to restoring torque, then the pointer comes to rest. That is the reason why your galvanometer pointer deflect like this, then come to rest. If no deflecting, no restoring torque will be there, then the pointer will rotate like this. Because the coil will rotate just like a motor. The coil will rotate just like a motor. Does it happen in galvanometer? No. Spring is connected. When deflecting torque there, then restoring torque also appears. And in equilibrium, bina is equal to K phi. In equilibrium, bina is equal to K phi. And it comes to rest. The pointer comes to rest. That is the equilibrium condition. And phi is equal to, I can write here, NBA by K into I. So, phi directly proportional I. Phi directly proportional I. If there is a current flow, then there is deflection. Then you can be able to know that the galvanometer works like this. If the current flow is there, then there is deflection. Some books are also writing this one, NBA by K as a galvanometer constant. Some books are writing NBA by K as galvanometer constant. You can write, but your NCT book is not writing like this anything. So this is about the galvanometer. But in galvanometer figure I didn't draw here. You can draw the galvanometer figure from your book, from your NCT book. So then let's come to here sensitivity of a galvanometer. Sensitivity means small action, more reaction. I told you, small action, more reaction. That is called sensitivity. Okay. So, small action, more reaction. Two galvanometers I will take. AB. Same current I will pass. 1 milliampere, 1 milliampere. This current deflects 30 degree. This current deflects 2 degree. Which one is more sensitive? Which current is more sensitive? Which galvanometer is more sensitive? Where deflection is more. For unit current, where the deflection is more, then that is called more sensitive. So sensitivity of galvanometer is actually two types. Two types of sensitivity. One is current sensitivity, one is voltage sensitivity. So let's discuss current sensitivity of galvanometer. The current sensitivity of galvanometer is the deflection produced more per unit current. Just before I told you, for same current in which galvanometer deflection is more, where the deflection is more, sensitivity is more. This is called current sensitivity, SI. Symbol we can write SI. This symbol varies from book to book. So if you bring the from the formula, it becomes NBA by K. NBA by K from the formula will bring. How will increase the current sensitivity? By increasing number of turns, by increasing magnetic field strength. We are doing that using soft iron core. By increasing area of the coil, but galvanometer will be bulky, so we will not write that one. By decreasing K, by decreasing the torsion constant, means we have to choose such material for the spring, such that K is as much less as possible. K value should be as much less as possible. Then the current sensitivity will be more. Then come to second sensitivity, that is voltage sensitivity. Voltage sensitivity. So voltage as V we can write the symbol. This is also the deflection produced for unit voltage. For same voltage in which coil more deflection is there. If you can write, we can write this phi by, this is IR. In place of V I put IR, where R is resistance of the galvanometer coil. Then phi by I, this is NBA by KR. So how the voltage sensitivity will increase? By increasing number of turns, by increasing magnetic field strength, area we will not discuss, by decreasing K, and by decreasing resistance. Resistance we decrease, we are taking the copper coil, no problem. Is it okay? Everybody understand how the voltage sensitivity also will increase? So a common, very important concept, a common mistake is there. I will tell from the common mistake, from this concept, one important question comes in exam. Most important question, 1 mark question comes in exam. Always this question comes. Frequently asked question, this one. Always asked. You mark somewhere, how will increase the voltage sensitivity? You see these points. Somewhere you did mistake. When I told you, somewhere one mistake I did here, but initially you can't able to detect where is the mistake, but now you go properly. By increasing number of turns, voltage sensitivity will increase. It will not increase. Remember, from the formula is just don't go superficially. Remember this one. By increasing number of turns, current sensitivity will increase. But by increasing number of turns, voltage sensitivity will never increase. Voltage sensitivity will not increase. Why voltage sensitivity will not increase? If you increase the number of turns, resistance, another term is here, it also increases proportionally. Resistance is proportional to length. If you increase more number of turns in the coil, accordingly the length of the wire increase, then accordingly resistance increase proportionally. Number of turns increase, accordingly resistance also increase proportionally. So, effect of number of turns doesn't change the voltage sensitivity. So, this number of turns has no effect on voltage sensitivity. So, by increasing number of turns, only current sensitivity will increase, but voltage sensitivity will not change because resistance increases proportionally. Remember. So, we can increase the current sensitivity, but voltage sensitivity will not change. Very important line, this one. By increasing number of turns, current sensitivity can increase, but voltage sensitivity will not increase because resistance increases proportionally. This is a very important point about sensitivity. Now will come. How will convert a galvanometer into ammeter and voltmeter? First, let's come to ammeter. How will convert one galvanometer to ammeter? Ammeter is a device which is used to measure current. It can measure current. large amount of current it can measure, but galvanometer cannot. It can measure very small current. So ammeter is a device which can measure very large current. Can galvanometer be converted into ammeter? Can galvanometer able to measure large current? Is it possible? Now not possible. What we have read from that portion, if you think it is not at all possible. Because in galvanometer range is small. Range means I am telling this one. If this is your galvanometer, I am telling range means this one. This is the last point. You can go up to this. Suppose this is suppose I will tell you 5 milliampere. This is 0. Then its range is 5 milliampere. Range means a maximum current which it can measure at the range of the device. Okay, so galvanometer range. Suppose I am taking one galvanometer, its range is Ig. Ig means it's very small. If it is very small, suppose 5 milliampere, and you want that your ammeter range is, suppose I will tell you 100 milliampere. Can the galvanometer able to measure this much current? If we pass this much current in the galvanometer, then what will happen? The galvanometer cannot withstand this much current. The pointer will go to the end and it tremble. The pointer will go to the end and it tremble there. So what happened then? Galvanometer cannot measure this much amount of current. Then what can you do? I am telling you one practical situation. So now you see. So this is a road. This is a road. This road has the capacity to manage some traffic. Suppose this road has the capacity to manage 100 vehicles. 100 vehicles can go through this road, or I am telling you 1000 vehicles can go through this road per hour. This is the road. 1000 vehicles can go through this road per hour. Okay, so this is the town road. Maximum 1000 vehicles can go through the road. But what happened? Due to some requirement, what happened here? Now every day as the traffic increase, what happened? Now around 5000 vehicles per hour are coming. Can they able to manage to go through this road? If they cannot go through this road, then what happened? This is a town busy road having a lot of shops. Many shops are there. Okay, so this road will be very busy. If this road will be very busy, what the government will take a decision? What decision will government take to manage this much excess traffic in this road? What decision government will take? Government decide those who don't have the work here in this particular area, for them what government did? Government made bypass. This is called bypass. Government made one bypass road. You all have seen on national highway many bypass roads are like that. Government made bypass road. This is the bypass road government made. I show it by black color. Okay, this is the bypass road. And this is the, what happened here? Maximum 1000 vehicles will go there. But through this side, how many vehicles will go? 4000 per hour. Now the problem solved. These 4000 vehicles has no work in this road. No work in this area. So they go through this bypass road and pass. Problem solved. It can't accommodate, it can't allow this much number of vehicles to pass. Then the extra vehicle go through this bypass road. Everywhere the bypass roads are there. Those who don't have the work in the town, but they have to go to the other side of the town, they go through this bypass. Everywhere the bypass. Maybe near your town, maybe some bypass is there. You can take the example of that. So the same thing happens here. I'm just giving the example. What is this? This is the town. This is equivalent to your galvanometer. This is, I'm drawing another figure. Let's keep your town like that. Okay. Let's keep your town like that. 1000 vehicles per hour. I'm drawing another figure. Okay. Just the role of this. This is the role galvanometer. It can manage very small amount of current I is just like 1000, and here current comes I, 5000 vehicles are coming. We'll do bypass. The extra amount of current I minus Ig will pass through here. A small resistance connected in parallel. It's called shunt. The process is called shunting, and this is simply we can tell in our common life example in electricians tell it as bypass. Okay, to pass like this. But why small resistance? I am giving you the example of this. Suppose this road is not good. Suppose this road is not a good road. Okay, so many muddy. So we can't able to go through this one, very muddy road, not a good road. Okay, if this road is not good, do you think this 4000 vehicles also will go through that way? No. There may be traffic jam, but they will enter through this. But when all the vehicles will go through this way, if the road is good, it's a very good road, having a lot of flowers at the side of the road, then these vehicles will go through this way. Because this road is very good. So for that we have taken less resistance. If you take less resistance, then more current will pass. More current will pass through this. This example what I gave you. This if 5 ampere go through this, 100 minus 5, 95 ampere will go through this. 5 ampere will go through this. 100 minus 5, 95 milliampere. 5 milliampere will go through this. 100 minus 5, so 95 milliampere go through this. When this more current will go, if the resistance will be less, then the current will go. Otherwise, the current will not go. Okay. So in this way, we can convert a galvanometer into ammeter by connecting a less resistance in parallel. This is called shunt. The process is called shunting. As a parallel, IgG, I minus Ig into S. Because potential difference is same in parallel connection. So how much shunt is required is IgG by I minus Ig. This much shunt is required to convert a galvanometer into voltmeter. You can do the numericals based on this. What is the resistance of this device? Whole arrangement. This is called ammeter. What is the resistance of this ammeter? Resistance is equal to resistance of ammeter is equal to as a parallel connection Gs by G plus S. Gs by G plus S. This is the resistance of this ammeter. But what is the resistance of one ideal ammeter? Ideal ammeter. I am telling you for that one thing. If you want to increase the range of this ammeter, then what you have to do? I am going practically. You see, 100 milliampere you are now sending. Suppose you want to increase this 100 milliampere. I suppose it's a 1000 milliampere. I want to increase the range of this ammeter. If 1000 ampere will pass, but this galvanometer will take maximum 5 milliampere, but you want 1000 milliampere. Sorry, we are doing in milliampere. If you want to pass through it 1000 milliampere, but it is allowing only 5 milliampere. The extra is, so earlier it is allowing only 95 milliampere. Now it has to allow 995. If 995 milliampere current will go, you increase the range of the ammeter. Listen, try to understand. Ammeter range increase. Ammeter range increase. If ammeter range increase, then what happen here? If ammeter range increase, then you have to decrease the shunt. Because more current will pass through this. If more current will pass through this, you have to decrease the shunt. If you want to decrease the shunt, you see, if shunt decreases, what happens to the resistance? Effective resistance of this ammeter. If S decreases, so in addition the effect will be less, but in multiplication, if a small quantity is multiplied, then this becomes again more small. So resistance of ammeter will be small. Resistance of ammeter will be small. See this one clearly. Very important, one more question comes in exam. If you increase the range of the ammeter, then you have to decrease the shunt. because all the current will pass through that shunt. Galvanometer will not compromise. If more current has to pass through the shunt has to decrease. If range of ammeter increase, then shunt has to decrease because more current will pass through it. If shunt decrease, then ammeter resistance also decreases. That's why more range, less resistance. Hence, if you compare the resistance, remember, if you compare the resistance, then ammeter resistance is less than milliammeter is less than microammeter. Remember, ammeter is lowest resistance, then milliammeter, then microammeter, then your galvanometer. Then your galvanometer. Okay, so this is the comparison of resistance of the four. And if you want to ideal ammeter, if you want to make ideal ammeter means ideal ammeter means it will not block any current. When you connect the ammeter in series, it will not block any current. That is ideal ammeter. Ammeter is always connected in a circuit in series. It has some resistance. Anyhow, maybe very, very small, but still it has some resistance. But if you want an ideal ammeter, ideal means it will not block any current it will not loss through it. Means its resistance is 0. Remember, ideal resistance, ideal ammeter has 0 resistance. 0 resistance. So this is about ammeter. Now we go to the conversion of ammeter into voltmeter. How we convert the ammeter into voltmeter? Voltmeter is the device which is used to measure potential difference. All of you know about this voltmeter. So let's connect. This is the galvanometer. Just reverse process. You have to connect a high resistance in series with galvanometer. Then voltmeter is made. Just the reverse process. This is your voltmeter. Why high resistance is connected in series? Because your galvanometer can't dissipate more voltage. If you want to dissipate your voltage, then you have to connect a high resistance in series because voltage divides in series. It can maximum dissipate 1 millivolt suppose, but your voltmeter is 100 millivolt. Then if you connect in series, then extra 99 millivolt will drop here. As maximum voltage it has to dissipate, it has to consume, it has to drop, resistance also has to be more. So in this process, a high resistance when connected in series with a galvanometer, it converts into voltmeter. V is the range of the voltmeter. Then what is the voltmeter range? V, Ig, equal to G plus R. Then from that you can find R, V by Ig minus G. We can calculate the value of R. The numericals will come. How much high resistance is required to convert a galvanometer into voltmeter? Range will give you, put the range. Then, what is the resistance of this device, this voltmeter? Resistance of this voltmeter is equal to G plus R because in series connection. And if you want to increase the range of a voltmeter, you want to increase. Range of a voltmeter. If you want to increase the range of voltmeter means voltage is more. If voltage is more, a galvanometer will not compromise. The extra voltage will drop here. So you have to increase R. If you have to increase R, then the resistance of voltmeter increases. More is the range, more is the resistance of your voltmeter. Remember, more is the range, more is the voltmeter resistance. So, if you compare the resistances, then what happens? Voltmeter resistance is more because more range, more resistance than your millivoltmeter, than your microvoltmeter. Okay, so resistance is more also than your galvanometer. At last galvanometer will come. So this is about the comparison of resistances of voltmeter. And if you compare the resistance between voltmeter, galvanometer and ammeter, voltmeter resistance is more than galvanometer, more than ammeter. Voltmeter resistance is more than galvanometer, more than ammeter. Galvanometer is middle, resistance increases voltmeter, resistance increases ammeter. So So this is about the conversion of a galvanometer into voltmeter and ammeter and the galvanometer part. The last part of this chapter is, we'll come to the last part of this chapter, magnetic moment of revolving electron. When one electron moves in circular path, suppose radius r, when the electron moves in circular path, it behaves like a current carrying loop. Because electron move means charge flow, behaves like a current carrying loop. It behaves like a current carrying loop. You know, current carrying loop behaves like a magnetic dipole. I have told you in the application of Bad-Savart law. It behaves like a magnetic dipole. It has two poles. It has a magnetic dipole moment. What is the magnetic dipole moment? I had told for current carrying circular coil to remember. I have told you one simple thing to remember. Nia. N-I-A. Magnetic dipole moment is Nia. We'll calculate the magnetic dipole moment for this revolving electron. You may ask the question, sir, can you give me a practical situation where electron moves and magnetic moment comes? It behaves like dipole? Yes, in your body. Your body or any matter consists of atoms. Inside atom, electrons are there. All the electrons move around the nucleus. So, all revolving electron behaves like a magnetic dipole. Each revolving electron behaves like a magnetic dipole. It has two poles. Create two poles inside the atom. Around atom, many electrons revolve. So many magnetic dipoles. You think about your body. You are made up of what? You are made up of atom. Iron, calcium in your body, they are there. In iron, many electrons are there. All electrons rotate around the nucleus, constituting one magnetic dipole. So that means you will be astonished that your body consists of only electric and magnetic field. Electric current, when the electron moves electric current, your body consists of only electric current and magnetic field. The only extra thing is there in your body, that is the soul. That is the soul. That we don't know made up of what. Rather, you are nothing but, you are not less than one robot. You are just like a robot consists of current and a magnet. Because each atom, many magnets are there inside the atom. Because each revolving electron behaves like a magnetic dipole. So, but electron revolve, electron move. Electron has two types of motion inside the atom. You know in chemistry. One is moves around the nucleus. One is it's a spin. One is a spin. One is azimuthal quantum number you are telling for its orbital motion. One quantum number you are taking spin quantum number. You may ask the question, so due to orbital motion, it has one magnetic moment. Due to spin also it has one magnetic moment or not? Yes. Due to spin also electron has one magnetic moment. But fortunately, due to spin what magnetic moment electron has, that is not in your CBSE board, CBSE syllabus. That is not in your plus 2 level. So we will concentrate on only orbital magnetic moment. Remember, but there is another magnetic moment called as spin magnetic moment. In higher class you will read that one. We will read only orbital magnetic moment. Remember. So orbital magnetic moment we will see. So what is the magnetic moment? So we write the symbol for this mu L. I use the symbol for magnetic moment capital M. But here I am writing the symbol mu L. L stands for your orbital azimuthal quantum number mu L. N-I-N. Nia. But N is one term. What is I? I is E by T because E charge flow in time period T and A is pi r square. So E, what is T? T is 2 pi r by V. Total distance 2 pi r and the speed is V. So I wrote 2 pi r by V. If you solve it, we will get EVR by 2. Pi cancel, 1 r cancel, then EVR by 2. This is the magnetic moment. EVR by 2. Okay. So magnetic moment of the revolving electron. But one thing you do here, you multiply one N here. you see what interesting thing comes. Multiply 1m. What is m here? Recall the Bohr's postulate in chemistry. Bohr's postulate. The electron can revolve in that orbit where angular momentum L mvr is equal to integral multiple of h by 2 pi. Recall your Bohr's postulate. You put there. So this mvr is L. This mvr is L. So mu L. L is the orbital magnetic. L is the angular momentum. Angular momentum. But mu L is orbital magnetic moment. And L is the angular momentum. Okay. So from this we can get one formula. Mu L by L E by 2m. It's a constant. It's a constant. E value you can put. Charge of electron 1.6 10 power minus 19. Then m is 9.1 into 10 power minus 31 kg. Then you will get a value, which is a constant. So can I say, where electron revolve in its orbit, the ratio of orbital dipole moment, orbital magnetic moment to the angular momentum is constant, and this ratio is called gyromagnetic ratio. It is called gyromagnetic ratio. It has a particular value. We will solve it and we will find what value it has, which is a constant called gyromagnetic ratio. Then in orbital magnetic moment, if I put the value of L, the expression of L, you see what happens. This is EL by 2m. Let's put the expression of L, NH by 2 pi. From here, you will get N EH by 4 pi m. Okay, EH by 4 pi m. So this is the orbital magnetic moment of revolving electron. But you mark one thing, N into something. N into something, you just recall. N into something. Charge N into something. What is this property called? You are thinking the answer. Quantization property of the charge. Similarly, orbital magnetic moment is also quantized. Because N into something. So it is also quantized, remember. And who did all these things? Bohr. Neil Bohr did all these things. Orbital magnetic moment is integral multiple of EH by 4 pi m. This is called orbital magnetic moment of revolving electron is also quantized. And what is the quanta? What is the minimum value? Mu L minimum. Just like charge minimum value is electronic charge 1.6 10 power minus 19 coulomb. Similarly, its minimum value is N is 1. You take 1 N1 EH by 4 pi m. You put the values of this. If you put the values of this here, you will get at last 9.27 into 10 to the power minus 24 joule for Tesla. This is the value. If you put here, you will get this much. You put the value of H, Planck's constant, M, mass, E, the electronic charge. So this is the minimum value of orbital magnetic moment, and it is called as Bohr magneton. This is called Bohr magneton. This value. So this is all about the chapter electromagnetism. So all theories we discussed about this chapter. Today we discuss about galvanometer and magnetic moment of revolving electron. Thank you.